we're off to a good start. All of my shortcut keys worked this time, so the setup went more quickly than it sometimes does. Okay, so the goal for today is to continue with 3-1 measures of center, and then start talking about 3-2 measures of variation. We introduced measures of center last time, and we'll start on measures of variation this time. What we'll also do some examples in Excel on 3-1 before we get to 3-2. So if I forget, if I jump right into 3-2 and get carried away, remind me that I want to do some examples on Excel. The Excel files are on Blackboard in the Excel file supplemental folder, but I also post them in chat, so they're easier for you to access that way, but you'll have access to them both of those ways. All right, the quote of the day for today is from the great Latin lyric or Roman lyric poet Horace in his book Satires. Our rough translation is that there is a mean in all things, too far to the right or left of which good cannot be found. So I thought it goes well with measures of center and the ideas of mean and so on. And mean and median both come from the Latin word for something like middle, or mean coming to us through French. So that's why it looks a little different. But so anyway, Horace, Satires, maybe try not to be on one extreme or the other extreme, but somewhere in the middle. That's usually a good place to shoot for in life in general, and also in academics, right? You don't want to be, for instance, you don't want to be overly narrow in the field you choose to go into. It's probably going to be a little tough to find a job if it's that niche, or if that niche kind of disappears for some reason, you're a little bit stranded. On the other hand, if you're so broad, if you're just going for something like communication or business or biology, a lot of times those kind of degrees, a lot of times, don't leave your degree just because they say this, but a lot of times those degrees can be so broad that it's a little hard to find your way with them. So, if you're going for one of those degrees, maybe looking at either creating a specialty for yourself for a minor, or taking classes in a certain field to kind of lean it one way or another. Maybe if you're in business, maybe you choose to go marketing, or maybe you choose to go finance or something like that, either officially or taking more classes in that direction to give you a little bit of depth in an area. So just one example of many that we could probably talk about related to that idea. All right, so last time, recall, I'll go through this quickly because we talked about it already last time. For measures of center, remember we were trying to answer the very vague question, what does a typical data point in our data set look like? And we always, from this point on, presume that we have a data set x1 through xn, where these are these are the data points. We have n data points. Different data points could have the same value. So I could have 3 different data points with the same value. So these aren't necessarily distinct values, but these are distinct points. These are distinct entities in our population. These are distinct people that we're measuring the heights of, or, people that we're counting the tax returns of, or people on different days that we're counting the tax returns of, or something like that. The mean, we had some notation that the sample mean, we call it X bar. Or if we had a couple of different data sets we were working with, maybe we have X1 through Xn and Y1 through Ym, then the Ys would be, their sample mean would be Y bar. So it's just whatever variable is representing that data set with a bar over it. And the population mean got this Greek letter mu. And if we need to differentiate between different data sets, we would put a subscript on the mu. So maybe, mu x or mu y, or in the case of Ashley and Brandon, we used mu a and mu b. Now, For Ashley and Brandon, we are told that these two data sets, tax returns per day for Ashley and for Brandon, are populations. We wouldn't know that just by looking at them if I just gave you the chart, but we're told that here. And last time we saw that mu A, which we get by just adding up all of the Ashley data and dividing by the number of data points added up, which is 5, was 8, and that was in units of returns per day. And Brandon's data set had the same mean. We also noted that it can happen occasionally that the mean is actually a member of the data set. But we don't want to take this question, what does the typical data point look like, too literally in this sense. We see that Brandon nowhere had a day where he got exactly 8 returns per day. We also mentioned that the mean corresponds to a center of mass. And this kind of question of whether the mean is part of the data set is a little bit like, if you imagine, say, a dinner plate like this, the center of mass will be the point where you'd have to put a support under it to balance it, and you could do that for a dinner plate. But we could imagine a washer, like that goes around a screw. Its center of mass is going to be in an area that there's no washer. There's nothing to actually support it there, right? It's in a sense impossible to balance a washer when it's flat. I mean, I guess you could balance it maybe on its edge, but when it's flat, it's impossible to balance a washer in theory, even though it is possible to balance a dinner plate because there's no support where the center of mass would be. So it's a little bit like that. The mean typically is not a member of the data set. And the last thing that we noted is that the mean has the same units as the original data. Very important point. We want to make sure that if we're adding numbers together that have units attached, then they have the same units. We talked in chapter 1 about the issues with inconsistent units a little bit, and we just want to check our units to make sure that everything's working out right and the mean does indeed have the same units as the original data. Okay, so that was a very quick crash course into what we talked about last time. Let's calculate the mean of the salary data. Well, the salary data we're told is a sample. So we're going to denote this mean by X bar, the sample mean. And again, we get the mean by adding up the value of each data point. 30, 100, 28.55, 28.25, and 28. So these are salaries in thousands of dollars for a sample of 7 folks taken from some company. I see that I added up 7 numbers, so I divide by 7. And I can go over to my calculator. Let me actually switch my screen share here. I can go over to my calculator, and this is where it's nice to have a graphing calculator. Oh, question in chat. Okay. So 30 plus 100, 28.55, 28.25, and 28. So I want to add these together. Now I need to be a little careful. If I just did divided by 7 like this, which I might be tempted to do, remember that these calculators respect order of operations, at least the graphing calculators do. So what this would do is it would say first do the division, 28 over 7, that's 4, and then add 4 to all these other numbers. That's not what I want. If I wanted to do this all in one line, I could use parentheses around the sum, and then after the parentheses divide by 7, Or what I like to do even better than that is just to add up my numerator. And now if I just, on this next line before I type anything in, if I just click the divided by sign, the calculator knows that I want to take my previous answer and divide by something. So it just uses this variable in the calculator a and s, its second negative sign down here next to enter, that refers to the previous answer. So I'm just going to take the previous answer divided by 7, and we get 42. The answer to all of life's questions, I suppose. If any of you have read Hitchhiker's Guide to the Galaxy. So again, just like the Ashley and Brandon data, this salary data had units of, let me hide my little zoom bar up there. Each of these has units of thousands of dollars. When we add them together, they maintain that same unit, thousands of dollars. We divide by 7. 7 is just a counting number. It has no units. So my sample mean has the same units as the original data, thousands of dollars. So my mean salary for this sample is $42,000. Any questions on the mean? And one last note, something that I might realize is that if I wanted to take, say, a measure of center related to shirt color observations where I have qualitative data, this data actually doesn't have enough structure to calculate a mean, right? I can't add red plus green plus yellow and divide by 10 or whatever it is. So I don't have enough structure there to compute a mean. To compute a mean, I need to have meaningful addition, right? I need to have the ability to add things, to combine things together in a meaningful way. So I need a little more structure to my data than just, say, qualitative or categorical. Okay, so what about the somewhat similar sounding median? So what's the idea of the median? The idea of the median is it's the middle number. So the median maybe is a little more direct or a little more literal interpretation of that question, a little more direct attempt to answer the question, what does a typical data point look like? Can I just pick the actual data point that's in the middle? Now, it is very important when I say middle number, I don't just mean whatever way that I happen to collect these numbers, I just pick the one that's literally in the middle. Because especially if I'm thinking of just randomly sampling, say, from the population, well, picking the middle number, it's just random what number that ends up being. That's really just the same as just picking one person randomly from the population. So very important. I want the middle number, but I want to order my data first. So the first thing that I'm going to do is I'm going to rearrange my data points in increasing data value. So let's take the Ashley and Brandon data. Let me copy this down. Fingers crossed. I actually had a heck of a time getting these all to copy over from the last sheet to this one. So fingers crossed this copy's okay. Like 80% of the time, OneNote copy is great. And then sometimes it just goes a little crazy. So if I was looking for the median of the Ashley data, the first thing that I would want to do is I would want to write the data points in order of increasing value. So I'll start with the smallest, 5. I'll write it down, cross it off. Then 7, 8, 9, and 11. And then how do I find the middle number, especially if I had a longer string of if I had 10 or 15 or something of these, I can cross off the smallest and the biggest. I cross off the next smallest and the next biggest, and I keep going until I get to the middle where there's only one left over. So I can just kind of keep chopping the ends off by one until I get down to where there's only one number left over. So the median for Ashley, which we'll just abbreviate as MD, median for Ashley is 8. And then since I just grabbed the value of a specific data point, I just took that value directly. That obviously comes with its same unit. A little side note, this doesn't really apply to our book or our class so much, but if you're poking around the internet and you're looking for extra resources, you might see this. Sometimes the population median is denoted by the Greek letter eta. It looks like a little N. So it's the Greek kind of like long A or E kind of sound, long E kind of sound. So sometimes you'll see that notation. Our book doesn't use that notation. We won't use that notation in this class. But if you're looking around and you see somebody, writing this other crazy Greek letter, this is the Greek letter eta, and that denotes the population median. I've never known of any notation for the sample median other than just writing MD. So, but we'll use the abbreviation MD for both population and sample median. We'll see that the mean will be very concerned with knowing whether we're talking about a population or sample mean, because we'll be connecting those two ideas with things like the central limit theorem and confidence intervals later on in the course. We don't have such a nice theory for the median that we're able to connect the sample median and the population median, and we'll actually see that also later in the course. So that's why maybe we're a little less concerned about denoting these very carefully, because just in practice that difference isn't as crucial. Let's do the Brandon data. So finding the median of the Brandon data, again, we're going to reorder the data set 3, 5, 7, 11, and 14. So we reorder smallest to largest. And then again, to find the middle number, kind of easy to find here, but if we had a longer string, we would cross off smallest and largest, cross off, or just write an X above or mark off or something. Cross off the next smallest, next largest, until we're down to just one left over, 7. So this is kind of interesting if we compare to the means, which I can't quite get on the same page. But remember that the mean for Ashley and Brandon were both the same, and they were both 8. So Ashley and Brandon have the same mean, but different medians. And also the Ashley data set has the mean and the median are the same, 8 returns per day, but the Brandon data set has a different number for the mean versus the median. Right. So this kind of brings up a question then, okay, I have 2 measures of center. Which one should I report as a descriptive statistic, and why? And we'll get a little bit more into that later. Let's bring down our salary data. Finding the median for our salary data, same thing. And again, just because we have 3 different data points that have the same value, we don't like just write that value once. There are still 3 different data points with that, so we do include it 3 times. And there I've gotten everything. And again, I can see there are 3 to the left and 3 to the right of 28. So the median for the salary data, 28, and that's in units of thousands of dollars. The median for the salary data is $28,000. And that's actually quite different than the mean of the salary data at $42,000. So we had Ashley where the mean and the median matched exactly. Brandon where the mean and the median were a little bit different. 1 unit on a scale of 7 to 8, 15% difference. But the salary data 42 to 28, that's like going from 28,000 to 42,000 is a 50% jump. So the mean and median can be the same, a little bit different, a lot different for different data sets. Now let's come over here to the salary data. And let's ask ourselves a question. What if, let's suppose that I had a salary data where I had only collected a sample of size 6. So just forget about that last data point. Just pretend that when we had collected the salary data, we had only collected these 6 numbers. What if I want the median here? Well, I do the same thing. Okay, 25, 28, 28, 30, 55, 100. And I do my same procedure. I chop off lowest and highest, next lowest and next highest. Now I'm a little bit stuck because if I chop off the next lowest and the next highest, I don't have anything left. And if I don't do that, I'm stuck with 2 data points. So how do I find the median for a data set where I have an even number of data points, where when I start chopping my way in, I always end up with 2 left instead of 1? Well, here I average these 2. So I add the 2 values together, I divide by 2. And this gives me 29. Note that these are both in units of thousands of dollars. 2 is just a counting number. It's the number of things I'm adding together. So the median in this case would be $29,000. For an odd number, for a data set with an odd number of data points, the median is always going to be a member of the data set. For one with an even number of points, it's kind of like the mean. Sometimes it will. If my 2 middle numbers had been 28 and 28, then my median would be 28 plus 28 over 2, or 28. So in that case, it would have been a member of the data set. But in the case that the 2 middle numbers are not the same, then when we average them, that average is not going to be equal to either of the 2 middle numbers, and we'll have a median that's not a member of the data set. So in some sense, the median is maybe more likely, roughly speaking, to be a member of the data set. Something like half the time it will be, and the other half of the time, sometimes it will be. Where the mean, usually it's not going to be. But the median is not guaranteed to be a member of the data set. Your book has, I think, an algorithm where you can do some computation with n the number of data points and figure out like the median is like x sub n minus 1 over 2 or n plus 1 over 2 or something like that. In my mind, it's not really worth remembering all of that because there's a different formula for the even or the odd. If we had to write a computer program from scratch to do this for a data set of size 100,000, then it would be nice to know that that formula, but that's not really where we're at in this course. That's not really our goal in this course. So we're going to be dealing with data sets of size maybe 10, maybe at most 20. And for those, it's easy enough just to go through by hand, write them on an increasing order, and work your way into the middle. And if you're on a physical piece of paper, you can even just, put your fingers at the end and then just move them in until you get to the middle, as long as you're careful and keep track of, moving each finger, one unit, don't move one finger twice or something and the other one once. So that's the mean and the median. Two other important ones are the mid-range and the mode. So the mid-range, again, I don't think that the mid-range gets any kind of special notation. So we'll just denote it MR, mid-range. And the mid-range is the average of the extremes. So where the median was kind of in some sense the average of the middle, the mid-range is the average of the extremes. It's X min plus X max over 2. The smallest data value plus the largest data value over 2. It's the average of the extreme data values. Or if we have done this ordering, which from this point forward in the course will essentially assume that our data is ordered in this way, where X1 is the data point with the smallest data value and Xn with the largest data value. We're going to say this is X1 plus Xn over 2. It's the average of the extreme data values. So the mid-range for Ashley, her smallest data value was 5. Largest was 11. And we see that Ashley's mid-range is 8 returns per day, the same as her mean, the same as her median. Brandon's mid-range, his smallest is 3. Largest is 14. So 17 over 2 is 8.5 returns per day for the mid-range. So Ashley's mean, median, and mid-range all turn out to be 8 returns per day. Brandon, his mean was 8 returns per day. His median was 7. His mid-range, 8.5. Let's look at the salary data. Smallest data value is 25. Largest is 100. So we have 125 over 2. That is, 120 over 2 is 60. And then 5 over 2 is 2.5. The mid-range for the salary data is $62.5 thousand. So let's draw these or write these out in a chart. So we have Ashley, Brandon, and salary. Mean, median, and mid-range. And I'm just going to leave off the units. We're not going to be comparing these directly to one another. We're not going to be comparing Ashley's data to the salary data, but we're just going to be looking at the differences between these. And then salary, what was it? 42. What was the median? The median was 28. And 62.5. Now, something we might notice also about these data are that actually if I kind of plot her data on a number line, so she has 5, 7, 8, 9, 11. So 5, 7, 8, 9, and 11. Here's that 8, that's the mean. And I see that her data is perfectly symmetric about this midpoint. This kind of midpoint of the data, this 8, her data is all symmetric about that. So this is for Ashley. For Brandon, he goes from what, 3 to 14. So he has 3, 5, 7. 11 and 14. And here is, for instance, Brandon's mean of 8. We can see that his 11 and 14 are kind of a little further to the right than maybe the rest of the data that's kind of clumped together a little bit over here. Maybe there's a little bit of right skewedness, although it's, if there is any skewedness, it's pretty minimal. The salary data going from 25 to 100. What should I do? Maybe 25 to 105 going in increments of 10. And what do we have? 25. This is 25 to 35, so 3 28s. 30. 55. And 100. This looks like a pretty canonical right skewed distribution. Remember, we talked about the skewness of distributions in chapter 2. So let's think about how this skewedness, and by the way, here the mean was somewhere down here around 42. So let's think about how skewedness affects these measures of center. So how does skewedness correspond to measures of center? Well, skewedness, remember, is when we have the presence of outliers and they're in one direction and not the other. So let's suppose that we have one really large outlier. How does that affect the measures of center? In other words, if I pretend that I go back to the Ashley data, instead of this being an 11, if it was an 11 million, something just off the wall absurd. If this was 11 million instead of 11, how does that affect the median? Well, if I come up here and, oh, sorry. No, okay, yeah. This is Ashley's data. If I come up here and if I make this 11 million, when I calculate the median, what's the first thing I do? I cross off the 5, I cross off the 11 million. The first thing it does is get thrown out. Whether it's 11 or 11 million or 11 billion, the first thing it does is get chopped off. The median doesn't care at all about outliers. In order for the median to care, you'd have to have like half of your data being outliers. And if half of your data are outliers, then they're probably not outliers, right? You can't say these are abnormal or unusual events if half of your data falls into that category. So the median is unaffected by outliers. The median's like an anchor. The outliers can exist on the left or the right or whatever. The median really doesn't care at all. The first thing the median does is chops off a biggest and a smallest, the next biggest, the next smallest. So all those outliers just get chopped off before you ever get down to the middle of the distribution where you compute the median. So what we have left is the mean and the mid-range. So the mean, let's look at the salary data, for instance. If this 100 became, say, 1,000, then that large contribution is getting divided by 7. Whereas down here in the salary data, if this 100 turned into 1,000, that's always only getting divided by 2. Since I almost always have a sample size that's bigger than 2, I mean, if I had a sample of size 2, that's certainly not representative. If I only have 2 numbers, why am I even going to try to report one number to you in the form of a mean? My samples are almost always bigger than size 2, usually size 7, 10, 20, 30, 100. So this denominator, practically speaking, is always going to be bigger than the 2 in the denominator in the mid-range. That means if I say have a large right outlier, it's getting divided, it's getting cut down in size by a number that is larger than 2 in the mean, but in the mid-range, that large right outlier is only getting cut in half. So the mid-range, an outlier affects this a whole lot. So significant or maybe substantial. And the mean, somewhat. So outliers affect the mid-range a whole lot more than the mean, and the mean a whole lot more than the median, which they don't affect at all. So what can I say here? I can say if my data set is right skewed. In other words, if there are a preponderance of right outliers, of high outliers, then I'll see that the mid-range will be much larger than the mean. So I'm using 2 inequality signs here to say much larger than. And the mean will be much larger than the median. So I'll see this ordering of these 3 measures of center because the mid-range will be pulled way to the right by those right outliers. The mean will be pulled a little bit to the right by those right outliers. And the median is kind of the anchor. It doesn't get affected by the outliers at all. And of course, if our data set is left skewed, then the mid-range is going to be much further to the left, much smaller than the mean, which is going to be much smaller than the median, which doesn't get affected at all. So I can say if the data set is skewed, then I know my measures of center are going to line up this way. I can use this idea to make a criterion for skewedness. I can take this idea and I can say, then if I compute my 3 measures of center and I see that the mid-range is much bigger than the mean, and that the mean is much bigger than the median, well, I might be tempted to say then the data set is right skewed. I can't exactly say that. This if-then statement, this implication goes that direction. if we have right skewedness, then the measures of the center line up this way. I can't exactly reverse that. So in terms of just pure mathematics, in terms of algebra or calculus or trigonometry, I can't say anything about what happens if the conclusion is true, right? Affirming the consequent, as they say, is a logical fallacy. So I can't say because mid-range much bigger than mean, much bigger than median, the data set must be right skewed. However, in statistics, we're looking for evidence in favor or evidence against. Statistical thinking, I mean, we're using a lot of, like hard and fast math, like 5 plus 11 is 16 every time. It's not, sometimes 16, but sometimes 15. So things like this, it's like the mid-range is always going to be 8 for this data set. Period, end of story. But when we're making conclusions, we're trying to go from data to information to knowledge, things get a little bit fuzzy. And we're looking for evidence in favor of something or evidence against something. So if I see my measure of the center line up like this, it makes me think, this is suspicious. Then I would say there's evidence in favor of right skewedness, or simply just evidence of right skewedness. I haven't concluded with absolute certainty that this data set is right skewed. In fact, I haven't even defined what it means to be right skewed sufficiently carefully that I could make that conclusion with certainty. But what I'm saying is if I see this consequent of right skewedness, or this consequence of right skewedness, then that gives me evidence in favor of there being right skewedness. In other words, had I computed my measure of the center and not seen this, I would not think that there was right skewedness. Since I did see this, that's kind of a point in favor of right skewedness. A little bit like the scientific method, right? We come up with a hypothesis, we try really hard to disprove our hypothesis. And if we're unable to, and if other people are unable to disprove our hypothesis, we kind of move forward and think that the hypothesis is correct. Similarly over here, if the mid-range is a lot less than the mean and the mean is a lot less than the median, then there is evidence of left skewness. I'm really harping on this because a lot of students get stuck here in statistics where sometimes we need to make to draw a conclusion based on the information that we have. Sometimes we have to make an argument in favor of our claim, of what we claim to be true. And sometimes there can be an argument on one side, there can be an argument on the other side, and there could be a healthy, good debate between people who know what they're doing and disagree. That can happen in statistics, right? Not likely to happen in algebra, right? That this solution to a quadratic equation, this is a solution or it's not a solution, and there's not really any debate there. But for something like this, well, even if we agree that this is satisfied, do we think that the data set is right skewed or left skewed or whatever? Maybe, maybe not. Now, of course, there's also another piece of subjectivity here. What do I mean by much greater than? Well, that's another issue. But even if two people agreed that criterion is satisfied, if they agreed that the mid-range was much greater than the mean and the mean was much greater than the median for a certain data set, they might disagree that there is right skewedness. This would be a point in favor of right skewedness, but somebody else might look at something different. They might look at the histogram or some graphical technique and try to make the call there, or maybe look at something that we'll even see maybe a little later in chapter 3. And these kinds of ideas are all over statistics, where we're not getting a clear black and white, you're either on this side or that side answer. We're getting kind of a fuzzy answer. We're getting an answer that says this points in the direction of this thing being true. So a very important idea, very important difference between the thinking in statistics versus the thinking in other fields of math, like say algebra or calculus or trig or something like that, where it's much more black and white, either right or wrong, end of story. Any questions so far? Okay, and then the last one of the M's is the mode. So let's grab this data set. So what is the mode? If I have the data, and this is my data set, these would be my x1, x2 through xn. They would be x1 would be red, x2 would be red, x3 green, and so on. The mode is the most frequently occurring data value. In other words, it's the data value that's the value for the most number of data points. So in other words, if I create a frequency distribution, I see that there are 5 occurrences of red, 1 of green, 2 of yellow, 2 of blue. The highest frequency is 5. Be careful, the mode is not 5. The highest frequency is 5. The mode is the data value associated with that. So the mode is R, or red if we wanted to write it out. The most frequently occurring data value in this data set is red, right? If these were shirt color observations, some fashion designer or buyer for a clothing store was sitting on a corner and just checking off the shirt colors that people are wearing, they saw more red shirts than anything else, than any of these other colors. Okay, so what if I wanted to come up with a different measure of center for this? Could I compute a mean for this? Well, no, because to compute a mean, I need to be able to add my data values, and I can't add red and green and yellow. Maybe I could do a median. Well, for a median, though, it's crucial that I order my data in increasing value. Otherwise, I'm just picking the middle one. It's just basically just randomly picking somebody from the population. Can I order these colors in any meaningful way in the sense of observing shirt colors? Probably not. Again, if you were a physicist studying lasers or something, well, maybe you could. Maybe you could say this one's higher energy than that one, and maybe these colors mean something different to a physicist in that context. But for most of the context where we're using things like colors in everyday life, no, there's no natural ordering or ranking here. Even we don't even have enough structure. We don't even have an ordinal level of measurement. Remember in chapter 1 we talked about all these, and it was like, why are we doing all this crazy stuff? Well, here's where it comes into play. We don't have an ordinal measurement. Even we can't impose a natural ordering or ranking, so we can't even do a median. So kind of the measure of center is what we're stuck with is the mode, the most frequently occurring data value. In this case, that would be red. So for this data set, the only measure of center we can really compute is the mode. Can we compute the mode for other data sets, though? Can we think the other direction? So let's consider our Ashley and Brandon data. What's the most frequently occurring data value for, say, the Ashley data or for the Brandon data? Unfortunately, each data value occurs once, exactly once. So what should we say? Should we say that there are like 5 modes. Sometimes we'll call something bimodal if like there were like 5 reds and 5 blues and a smattering of green and yellow. We might say that that's bimodal and that red and blue kind of tied for the mode. But when do we stop adding in new modes? Is there a trimodal? Is there a whatever will be the next one? I don't know. So the mode is a little ambiguous or a little confusing when you get to numerical data like this. Or if we look at, the salary data, maybe the mode actually does make a little more sense in the salary data. We happen to have 3 28s, and those 28s are kind of at the middle of what we might call a typical data point. In other words, if we're ignoring the outliers, a lot of the data is located around where that mode is. That might seem reasonable. But these are also salaries. We might have rounded them to the nearest 1,000. Maybe this person is made 27,925, and this person made 28,105, and this person 28,300. Should 28 not be the mode then? Right? It's kind of difficult to say. Or in the worst case scenario, what if we're rolling a fair 6-sided die? Right? So we have in theory, a perfectly uniform distribution where each number 1 through 6 comes up equally likely. But if I actually roll this die, let's say 10 times, one of them is going to come up just a smidge more than some others, right? Maybe this one comes up a little bit higher. Well, then I would say this is the mode because it beat all of the others by, it's a little taller than all the others. But that was completely random. So maybe this time I get a mode of 1, but next time I happen to get 1 additional 5 and 1 fewer 1, and now this is the mode. If I have data where, in a sense, the number of bins, so to speak, the number of possible divisions is much, much larger than the number of data points that I have, or if I have a data set where I think that the population that I'm drawing from is kind of uniform, then whether I draw a few more of these and a few less of these, that's just completely random. The mode isn't really a good measure of center in those cases. The mode would basically just be completely random. If actually it happened to get, 7 returns this day and 10 that day, then all of a sudden her mode is 7. So the mode isn't always a great measure of center. In fact, I would argue that for practical purposes, it's usually not a great measure of center, with 2 exceptions. One is for qualitative data, where we don't really have any other approach. And the other is if we have this kind of like theoretical frequency distribution that we'll talk about in chapter 6, where we have a nice continuous curve where there's a very clear maximum, then the mode is pretty well defined. So if we have qualitative data, especially qualitative data that doesn't really come from a uniform distribution, or if we have frequency distribution like this, the mode makes a lot more sense then. When we have actual data values like these, probably something like a mean, a median, even a mid-range is going to be a much better measure of center than something like a mode, which is probably just kind of random. It's just kind of buffeted around by chance, whether we get a collision between 2 observations or not. But what the mode is really trying to do is it's trying to tease out, like, do I see clusters of data? That's what it's trying to do. And in practical data sets, it's a little hard to say whether we have a cluster of data here just by looking at how many of the exact same data values occur. So it's actually kind of an interesting AI machine learning problem trying to cluster things. So there's like k-means clustering and all these different clustering algorithms. If you're into computers and IT and all of that, interesting little topic. trying to figure out what the natural way to cluster data together is into different groupings. But that's kind of what the mode tries to do, is it tries to cluster, but in practice, it maybe doesn't do it very well in a lot of circumstances. But it is very important in these two ideas. The highest point on, say, a continuous curve, or as at least something you can do to a qualitative data set to get an idea of a measure of center. It's about all that you can do to something qualitative. Okay, so I think before going on to these, I want to jump into Excel, make sure we get this in, and then these three might talk about a little more, a little less, or I might even just post a supplement on those, depending on how much time we have. So let me first pop these Excel files into chat. So these are the two Excel files we'll be using today. It looks like they uploaded, so that's good. They're also on Blackboard under supplemental materials and Excel files in chapter 3. And we'll start with this one. Oh. Go to this tab. There's different tabs at the bottom here. We'll go to the one that says datasets class, datasets for this class. And we have a little bit of extra stuff over here related to those other means that we haven't talked about, but mainly we have the Ashley and Brandon data and the salary data populations and a sample. And let's compute our 3 measures of center for these 3 data sets. So for mean, I can do equals average. Remember, anytime I want to tell Excel that, hey, I want you to interpret the thing I'm going to type as a calculation or as a function evaluation or something like that, I need to start with equals. And then if I want to refer to one of Excel's built-in functions like average, I just type the name. And often if you kind of don't quite remember the name, you can, you're like, is it AVG or AVE or something? Or you can start typing it and you see that a list populates here and there's average. So average, and you can either hit tab to kind of autofill the rest, or you can type average, open parentheses. Remember, just like functions like f of x equals x squared, f of 2 equals 2 squared, the input goes inside of parentheses. So we have this function average that we're going to evaluate at some input, and the input is going to be the Ashley cells. I'll select those and close parentheses. So it equals average B2 to B6. And that gives me a mean of 8. Now I could try to drag this down and change this to median, but again, that changes my cell references. If I want to, I can, if I drag this down, I can double click, and then actually, if I hover over the edge of my box, this blue here box, and I double click, I can drag it back into place. So if you ever, if you're ever selecting some cells and you miss one or something, or you get one extra, you can manipulate the size of this box using either the corners to make it bigger or smaller, which I apparently did not grab that corner, or using the edges to actually move it around. But if I do that, that's kind of a lot of work. Maybe what I can do is take the Ashley data and give it a name. Maybe I'll call it A data or Ashley data. Remember, we did this last time. So just selecting the cells that I want to refer to for Ashley, and I see that I've named that A data now. So I can come down to median. The Excel function for the median is median. And if I start typing in A data, I see that it comes up in my list here. I can just hit tab to auto-complete that. And I can verify that it did indeed select the data that I'm interested in. Ashley's median is also 8. We could name Brandon's data B data. I think I maybe had already named it Brandon, but I just renamed it B data. And I could do the same thing down here, equals average. And I start typing in B data, and there's my B data. And there's nothing special about the variable name that I gave it. I just called it B data because that was easy for me to remember. If you wanted to call it Brandon, or if you wanted to call it, data set 2 or something, whatever you want to name it is pretty much fine. So average of B data and median of B data. I don't know why it's sometimes making that into a lowercase. I've never seen it do that before. All right. Microsoft always confuses me, but it works just fine. And it still has the uppercase up here. So I guess it just didn't like that I had 2 caps next to each other for some reason. So mid-range though, well, mid-range, there's not a built-in Excel function like equals mid-range that I can use. So I've got to kind of go back to basics for this one. And remember, the mid-range is, well, it's x1 plus xn over 2, but Excel doesn't know about x1 and xn. But really, it's the minimum data value and the maximum data value, the average of those. Excel does have, say, min of Ashley data. It does have a built-in function min for minimum and max for maximum. So I can use these built-in functions min of A data plus max of A data. Now here, if I just divide by 2, which I might be tempted to do, again, be careful, Excel does respect order of operations. So this would take the max, 11, divide that by 2, get, what, 5.5, and then add the min, which is 5. I need to use parentheses, another set of parentheses on the top here. So that I have min plus max done first, and then divide by 2. And this gives me my 8 that I expect. That was a lot to type in. I can drag over. Now this still refers to the Ashley data that's up here. I'm trying to hover over, but still refers to the Ashley data. But it might be easier for me to just change those to the Brandon data, B data. And get the mid-range for the Brandon data. As I mentioned last time, I'm going through this Excel stuff somewhat quickly. Probably the last time I'll say it, but the caveat is, if this is your first time seeing Excel, this is way too fast. But that was why I mentioned before, there's the free Coursera course that you can take a look at. You can follow through the steps in the book, get acclimated to Excel that way. You can just, Google how to do things on Excel. But if you're not somewhat familiar with Excel, this is going to be way too fast. And if that's the case, this weekend, get a little bit more acclimated with Excel, get used to poking around with it, and then come back to this lecture and the last one where we did some work on Excel and review these topics, follow along with me, and then it'll be at a more manageable pace when you're more used to it. Let's see, I think there's a question in chat. After dragging the number, what do you click to see the formula? Oh, so if I am on the number 7 here, how do I see what the formula is? There's 2 ways to do it. One is up top here, see above column C, there's the formula bar. So that tells you what is entered in there. So this formula bar equals median of B data tells you what is generating that number 7. If you either click this formula bar Or even better, if you double click the cell, then it'll show you right in the cell what the formula is that's calculating that cell. Now, when you're in a cell, if you click out of a cell, sometimes it does that, which is super annoying. If you ever get yourself in that situation, just hit escape. So when you're in a cell and you're like, okay, I'm done with being inside of the cell, so to speak, just hit escape to get out of the cell. That messes me up constantly because if I'm on Excel and if I hide my Zoom meeting panel, escape is it's the command to both get out of the cell in Excel and to show my Zoom meeting panel. So I hit escape, but the Zoom takes precedence. So then it'll show my Zoom meeting panel and then it'll pop up over my stuff. And it's kind of funny. Yeah, the escape button, like on the top left of most keyboards. So if I'm in the cell, I don't want to just click out of it because, well, that time it worked okay, but well, now I can't get it to break. But you saw before that it like, yeah, so sometimes it'll do something like that. It's like, well, so if I click out of the cell, sometimes it thinks that I'm referring to a different cell that I want to input into the formula, but just hitting escape kind of closes you out of that. There's also one of the F keys, and I don't remember which one it is off the top of my head, but it'll actually toggle all of the cells to show you, instead of displaying the number that's calculated, to show you the formula. It's one of the F keys, but I don't want to go hitting all my F keys because some of them do crazy stuff. So I'll end up, frying my computer or something. But one of the F keys will toggle everywhere that there's a formula. It'll just show the formula instead of the number that's calculated. I've never really felt the need to do that, but if you got, somebody else's Excel file, like if you downloaded this Excel file and you're trying to follow along with the one that's completed, maybe that's something that's helpful for you. I don't know. Okay. So let's go to the second Excel file. This one, chapter 3, data analysis demo. And we'll look at one more thing. And as an aside, here's just for last digits of weights, here's the bin set up. So if you wanted to, you could poke around and play with the histogram. Can't get my windows to cooperate. There we go. In data analysis, we talked about this last time. Histogram is an option in here. My cursor is just doing crazy stuff. I could choose an input range, all my data. I will include labels. And then my bins, because I included labels, I'm going to choose my bin range, including that label. New worksheet ply. We'll chart the output. This will give us a histogram. Hit OK. And then we get this picture. And it always includes this annoying more line, but I guess we can get rid of that. And this basically gives us the histogram we are interested in. If we wanted to, we could adjust the data set just by changing the size of those boxes. And there's our histogram for the last digits of weights. So we mentioned that last time. I don't think we actually worked through that. But if you want to, you can practice that. But here we have last digits of weights, and I would like to get descriptive statistics for this data set. So I'd like to have Excel just print me out a list of a bunch of interesting things I might want to know: the mean, the median, the number of data points there are, things like that. If I go over here to data analysis, and if I go to descriptive statistics and hit OK, my input range, last digits of weights, I will include the label, and then I'll shift click to go all the way to the bottom. So I click the label at the top, shift click all the way to the bottom. That selects, well, I accidentally tapped instead of scrolling, but that selects cells A1 to A51. Labels in the first row, so I note that I did tell it a label, so that way it'll label my my output. I'm going to output to a new worksheet. I could, like, if I wanted output range, I could pick a cell or something in this worksheet where I wanted to plop all that data, but I always just do a new worksheet. And we'll do summary statistics. There are other things you could do, like confidence levels, things that we'll get to later in the course. Or if you wanted like the third largest and the third smallest data value or something for some reason. But right now we'll just do summary statistics. And I see that it printed this out for me. I can't read half of these things. If I want to resize a column, if I go up here to like see if I hover over A, it selects A, and I could click on that and select all of column A. Or same for B. If I'm right between A and B, my down arrow changes to like a left-right arrow kind of deal. I can double click and use that to change the width of my column, or I can just double click on that. And my column will automatically size so that I can see everything. Some things like standard deviation and variance we'll talk about in section 2. We've already mentioned a little bit about skewedness, and we see there's a number associated with skewedness. So maybe this indicates to us that that's something that is maybe coming down the road. Range, also in section 2. We see max and min. That's nice to have. Count, just the number or the sample size, the number of data points. But mainly we see the mean, the median, and the mode. Mean of 2.48, median of 0, mode of 0. And again, because more than half of our data are 0, because if people are self-reporting their weights, they're probably reporting it as like 150 or 190 or something, and not 192.5 or some crazy thing. Since more than half of my data are 0, that's the median. That also happens to be the mode. And I see that the mean is about 2.5. So if I look at my histogram, 2.5 between 2 and 3, that would be kind of the balance point here. This kind of feels like it might be a little bit right skewed, right? If I think of the quote middle of my data set as being something like the mean, the mid range is going to be 5, the mean 2.5, the median 0. Maybe 5 is a good bit bigger than 2.5. It's twice as large. And 2.5 is maybe a good bit bigger than 0. Maybe I would think this is a right skewed data set. That's a little bit of a tangential note, but we see our descriptive statistic computed here, along with some others that will be helpful in later sections. That's about all we'll do on that sheet. There are some other tabs on these that sometimes I talk about if we have a little extra time, but since we're running a little bit short on time, we will move on. So we've got about 25 minutes left. So let's talk about the weighted mean. And we'll use this data set. We'll work with this data set for the weighted mean. So what's the idea of a weighted mean? Well, for a weighted mean, I have some data. I have n data points with each of which has a data value. But I also have some weights. A weight is a number that corresponds to each of these data points. So W1 corresponds with X1, W2 with X2, and Wn corresponds with Xn. And these weights can be any positive number. I guess you could have a 0 weight if you wanted. They could be any non-negative number. A lot of times we choose weights between 0 and 1, so it's kind of like a percentage, but it doesn't really have to be. Then the weighted mean is going to be W1 times X1 plus W2 times X2, and so on, plus Wn times Xn, divided by the sum of the weights. And something that's pretty standard is to set up your weights so that the denominator is just 1, so that all of the weights sum to 1. If the sum of the weights is 1, then I don't have to worry about that denominator. If the sum of the weights was not 1, I could always just rescale. I could think of this as like W1 over W1 plus W2 all the way out to Wn times X1 plus W2 over that, X2, and so on. And I could just call this like W1 tilde, X1, W2 tilde, X2, and so on. So I can always just rescale my weights. I could take each weight, divide by the previous sum of all the weights, and then that just rescales the weights. It doesn't affect the outcome of the weighted mean at all, but it just makes it a little easier for me to deal with the calculations. So often we choose weights that sum to 1 for that reason. And we'll actually see this idea of weighted mean generalizes a heck of a lot when we get to chapter 5. Chapters 5 and 6, really. But what's the idea here? Well, sometimes we want to count some data more heavily than other data. We want some data to contribute more or to have more impact than other data points. This might be something like, let's say we have, different radar stations, say in the US. In the US, we probably have a whole bunch of different, let's say, temperature monitoring stations. But out in the middle of the ocean, if we're interested in temperature, we might only have a couple of them. So if I'm trying to come up with something like what's the global mean temperature right now, well, maybe each one of these temperature stations in the US only accounts for a relatively small area, a relatively small amount of geography that it is kind of sampling for. But each one of these in the ocean maybe has to account for a much bigger region. Maybe I want to weight these numbers differently. I don't want to just take all of my 1,000 temperature data points and weight them evenly, because then I'm kind of like over counting the stuff that's in the areas that are in populated areas on land, where there might be a preponderance of temperature stations, and I'd be undercounting, out in the temperatures out in the ocean. So I might want to adjust the weights so that I weight each data point according to kind of the geographic area that it's in a sense representing. Or an example that ties directly into this course, although these aren't exactly the weights for this course, but is something like this, where we have different assignments. We have homeworks, quizzes, midterm exam, and final exam that are worth different amounts, right? Quizzes are worth, again, not in this course, don't be worried that you missed a quiz or something like that, but just as an example, in some course, maybe quizzes are worth only 10%, but the final exam is worth 40% of the final course grade. So you can't just take your scores add them together, divide by 4, and that's your course grade, that doesn't respect the weighting. If you did really well in the final and really poorly on the quizzes, your grade would be a lot higher than vice versa if you did great on the quizzes and really poorly on the final. Now I have to be careful. Number one, which ones are the weights and which ones are the data points, because I need to know which ones I'm dividing by. And number two, I have to be careful to make sure that the weights and the data points correspond correctly. So homework, we'll call this W1 30%, and then X1 for homework, score 90%. Quizzes, midterm exam, and final exam. So what's this person's final course grade? Well, it's weight 1 times data value 1. So that's 0.3 for the weight. I'll leave the data values in terms of their percent. So I'll leave it as 90. And I'll just consider it as carrying the unit of percent. So our number at the end will have a unit of percent. Plus W2, 0.1 times data value 2 is 50 with the unit percent. W3 is 0.2 times 75. And W4 is 0.4 times 80. Then we divide by 0.3 plus 0.1 plus 0.2 plus 0.4, but nicely enough, these add up to 100% or just 1, so we can ignore that denominator. Let's come over to the calculators, to the calculator. So we have 0.3 times 90 plus 0.1 times 50, 0.2 times 75, 0.4 times 80. Let's just double check that all typed in right. Again, super nice thing with these graphing calculators. I can just look back and forth and check everything. That looks good. And this gives me 79. And remember with that unit percent. So my final course grade for this person would be 79%. So now what if, say we're halfway through the course, and what if this person doesn't have a final exam score yet, but let's say they did score 75% of their midterm exam, their quizzes up to this point average 50%, and their homework up to this point, halfway through the course, average 90%. What if we want to give them a midterm course grade? One way that we could assign a midterm course grade would be to say, basically, if I had to give them an average that is a weighted average based on what they completed so far, they haven't completed the final exam, I could give them a weighted mean based on just these 3 data points. So here, the midterm course grade, in this sense, what would it be? Well, W1, X1, 0.3 times 90, plus W2, X2, 0.1 times 50, plus W3, X3, 0.2 times 75, divided by the sum of these 3 weights. But now the sum of these 3 weights is only 0.6, right? There's only 60% of the material that's been covered so far because we don't have that 40% from the final exam. So I can't just use the numerator here. I have to divide that by 0.6. Since a lot of the calculation here is the same as the one above, I want to copy this line down and then just work off of it. If I do second enter, that brings up my previous entry, as that yellow bit says there. So second enter, super nice operation to use with a lot of the stuff that we'll do in this course. Now I see I want 0.3 times 90 plus 0.1 times 50 plus 0.2 times 75. I don't want these last, oh, a little too far there. I don't want these last bits here. I do want to insert a parentheses at the beginning. So I'll do second delete to insert a parentheses. And I want a parentheses at the end. So I have the whole numerator divided by 0.6. And I see this is 78.3 or so. And again, that carries a unit of percent. So the midterm course grade for this person, at least computed this way, would be 78.3% on the basis of these 3 data points. Now, one kind of aside, and this is where the kind of art of statistics comes in, or the gray area comes in. Is this a good choice of number for the midterm course grade? If I was going to report this to somebody and say, this is your midterm course grade, is this a good choice? And the answer is it's kind of complicated, right? What's the purpose of a midterm course grade? If the purpose is to give you an idea where you stand in the course. So if you look at that 78 and you're disappointed, if you thought you were doing A work, then maybe you need to work a little harder to get up to an A by the end of the course. Or if you thought you weren't doing so great in the course and you've been, working hard and just felt kind of down, and you see that you're almost at an A, that might tell you, okay, you're actually doing really good. Keep doing what you're doing if you want to maintain this. That's kind of the idea of a midterm course grade. It's halfway through the semester, so you've got plenty of time to kind of course correct if what you think is going to end up being your final course grade, if you keep doing what you're doing, if that's not in line with what you expect or what you want. But then the question is, okay, well, this homework score of 90%, that doesn't include all the homework in the course. That's only the first half of the homework. In these quizzes, maybe that's only half of the quizzes for the course. But the midterm exam is like all of the midterm exam, right? In other words, at the end of the course, this midterm exam number is still going to be exactly 75%, regardless of what you do. But if in the second half of the course you try really hard and you do great in your second half of your quizzes and homework, these scores might go up by the end. Or if you do poorly on them, they might go down. So the homework and quizzes only really count for, I've only really accounted for half of those so far, but I've accounted fully for the midterm exam in the actual course. Should I reweight these to be 15% and 5%? Or should I go the other direction? Should I say, well, if your midterm exam score was 75%, I can use that as a proxy, as a guess for what your final exam score might be. Maybe I would say if you did a similar performance on your final exam as on your midterm exam, you would get a 75 on your final exam. Should I make this a 75 and fill it in to show you, if you did similarly on that exam to your midterm exam, what would your final score look like? These are all reasonable things to do. These are all things that a person could do, and a person, could say that they think this or that is the better way of computing a midterm course grade, and there's not really a right or wrong answer. That's one reason that I don't like midterm course grades so much when I have to compute them for students every semester, because there's just a lot of gray area. There's a lot of decisions that have to be made, and it's unclear how to make those decisions. So the reason to tell you this is when you look at your midterm course grade, if you see a B, don't lock into the idea that it's a hard and fast black and white kind of B. The final course grade is a hard and fast black and white. Once everything is turned in and everything is graded, this is the computation. For midterm course grades, there's there's as much art to it as science. And just as an aside, since we don't have quizzes, we have exams and homework. And since our midterm exam falls after the midterm course grade, the midterm course grades are due, I just take your homework average. That makes it simple for me. That makes it simple for you to understand. And then you can take your midterm exam score that'll come out, maybe a week or two after that. And you can incorporate that whichever way you feel comfortable. So whatever way you would like to do it best, whatever you think gives you the best idea of how you're doing in the course, you can take those components and combine them whatever way works best for you. But I wouldn't lock onto, either in my class or in any other class for that matter, I wouldn't lock onto those midterm course grades too tightly, but really take it as more like, if you think you're doing well in the course and you see an F or a D, something's probably wrong. You want to check in with your instructor. If you think you're doing okay in the course and you see an A, like, great, you're doing better than you thought. That I would take it as a very coarse measurement, not a very fine, precise measurement. Because again, there's just a lot of gray area here that us as instructors need to decide what we're gonna count, how we're gonna count it, how we're gonna weight it, all of that. So we didn't quite get to section 3.2, but I am happy that we got through a lot of that information on Excel. That'll make when we do Excel for 3.2, that'll make that go a little more quickly. And we'll leave geometric and harmonic mean. I think probably what I'll do is post a supplement on those. Just those two are pretty quick to get through. They're pretty straightforward. So I'll probably just post an extra little YouTube clip, probably 20 or 30 minutes or something, talking about those. I'll probably actually just take a clip from a previous class meeting if I can find one, or I'll just record one new for geometric and harmonic mean to wrap up 3.1, and then when we come back, we'll start right into 3.2. Probably finish that in one class meeting, and then we'll start 3.3 next time as well. So take a glance through 3.2 and 3.3 for next time. That wraps us up for today. Are there any questions on anything that